Ben.
Hi, Matt.
How you doing, buddy?
I'm doing pretty good.
It's been a while. We've been talking a lot about testing recently. So, what do you think to mixing it up a little bit?
Yeah, we should not talk about testing today.
I mean, we are quickly becoming all test all the time podcast, which wasn't really the original intention of this podcast. Although
No,
an important,
it's mostly my fault.
Well, I mean, it's kind of your thing, right? You're the test person.
Yes,
or a test person.
I'm very testy.
You're very testing at times. No,
Yeah.
never testing. And we when we were discussing this podcast initially, like you and I were thinking, the thing that we would like to do is bring along kind of like audiences that would by default follow us for the kind of things we're known for, and then show them something different.
Mm-hmm.
You know, get some people on that can talk about something that maybe they aren't as familiar with, or just dig into something that's just interesting to us, right? I mean, that was the idea. And then we started talking about testing, and we carried on talking about testing because there's just so much to talk about, and it's really not very well understood and not very well implemented. And, you know, you and I have seen a lot of it done well and a lot of it done not so well. So let's talk about something else.
Yeah, I want to hear about the chip reverse engineering stuff that you've been looking at for, I don't know, probably quite a while now, right?
Well, yeah, it's one of my hobbies has led me down a very strange path.
Mm-hmm.
And so I grew up in like the late 80s, early 90s with a computer from Britain, and for whatever reason, I've ended up taking a trip down memory lane and writing an emulator for that computer.
Mm-hmm.
And the thing about writing an emulator is it's an amazing way of understanding fundamentally what a computer is and how a computer works and how the peripherals work. And if for example, you don't have an instinctive understanding of that, or if you've never actually written an interrupt handler, and frankly, who has, or that level of things, but you're interested in that side of computing, like how they actually work, you can go a lot far worse than writing an emulator. It's a great way of giving you that exposure while in the familiar, warm embrace of a modern IDE and the sort of debuggers and all the things that come along nowadays.
Mm-hmm.
And in particular, I was the emulator that I wrote for the BBC Micro, which was a computer in my school when I was 10, 11. The emulator I wrote, I chose to write it in JavaScript, which is not noted as a systems programming language. I think it's fair to say.
Yeah, it does have that reputation as not a systems language.
Right.
Yeah.
But what it is you know, universal, and more importantly, you can put it in a website, and then you can play your video games from your childhood in your web browser. And what's not to like about that, right?
Right.
But the thing about emulation is that there is a kind of a period at the beginning when you're writing a bunch of code and you're kind of doing it blind. You're just kind of taking it on faith, pretty much, that you're emulating this particular facet of the CPU. And you've got a big table of these things, right? There's a huge list in your lap of the opcodes that the CPU runs. And you're like going through them one by one, or you're hopefully coming up with some level of abstraction to make it a bit easier. And then you're writing peripherals and bits and pieces like that. And there's this one joyous moment when for the very first time you load up a ROM and you execute it, and something recognizably associated with what you're emulating happens.
Something game-like happens. Yes.
In the case of this computer, when you first turn it on, there's a sort of very familiar to certainly people of my age and from Britain sound that comes out, and then a particular sort of text comes up. Like you think of a DOS mode black screen with just ASCII text on the screen saying BBC Computer 32K, Acorn, MOS, Basic, and then a prompt, and then, you know, that's it.
Right.
Now, because the hardware, at least for this particular default video mode, is essentially ASCII mapped, that meant that all I could do is I could plumb a routine in JavaScript that just runs through the memory area associated with the screen and dump it out to console.log. And so I was able to see BBC Computer and all that stuff appear in the console before I had anything else gone. But it's, you know, so it's a marvelous thing to do. And it's so rewarding. And as you add more bits and pieces, you get more functionality. Eventually you get like bitmap graphics, and then you can get the joy that you mentioned, which is playing games. And that's fun. That's super fun. But what you've kind of start doing is realizing that the manuals that you've got, or the memory of how computers work you've got, is incomplete and wrong. And some of the video games of yesteryear, maybe less so today with more random hardware available, but back in the day, video games programmers would discover weird things that the graphics chips did, or the CPU did, or the interrupt system did, and they would incorporate that into their game, or they would incorporate it into the copy protection for their game, so that it was really, really hard for you to either copy or hack, or they got extra performance because they were relying on some extra weird thing. But of course, everyone had the same physical hardware, so they could genuinely rely on these kinds of things. But you didn't know that as an emulator writer.
Right.
So you just emulate it like it says in the 6502 manual. It says, yeah, well, this sequence of bytes is meaningless. It's not used. And so you don't do anything with it. And then you discover games, and you've hit your debug trap that says, no, some game used that opcode, and you're like, what?
Yeah.
The first time I hit this, it was, I think it was, the first time I hit it was in a game called Repton, which is like a Boulder Dash kind of game. And as part of the code, it actually jumps to an ASCII string, right? It starts interpreting an ASCII string as bytes. Now, as it happens, that doesn't have any meaningful side effect, but there are all these undefined opcodes in there. It doesn't do anything. And eventually it falls through into the real code and carries on. And whether that was intentional, whether that was a mistake, I don't know. But it was like a first wake-up call to like, hey, well, it doesn't like stop. These computers didn't have the facility to like throw an illegal instruction exception at the hardware level or anything like that. They just plowed on.
Yeah.
And of course, it's all logic gates at the end of the day. And so those bit patterns still meant something to the hardware, and it did something. And so the game designers would discover that, hey, if I use this opcode, it's the store instruction, but with one bit different. Now, normally there's store A, the A register, store X, store the X register, store Y, the Y register, and then in the sort of fourth, if you were literally just looking down the list of opcodes, there was like, no, don't use that one. And then it went on to the next instruction.
Yeah.
And of course, you're thinking to yourself, wait a minute, any normal human being who was designing this would see that essentially the only thing that was changing from one instruction to the next are the bottom two bits. In the store A, it's 00, store X, it's 01, 10, and then 11. You're like, well, what the heck is this doing? And so it turns out that through whatever means, people realize that what's happening at that point is it's storing A ANDed with the X register. And now I have literally no idea why that would be useful in a game context. Maybe for masking, actually, now I think about it. I can't believe I've never thought of this before. But if you had like a sprite mask in the X register, you've saved yourself an opcode, right? You don't have to AND with the A register and then store the A register. Use this SAX command, which isn't, again, it's not an official thing, but it just comes out because that's the way the hardware physically works.
Yeah.
And so you start finding out more and more of these things. You start realizing that the systems are not as well understood as the manuals would have you believe. They're not as well as understood even as the designers of the original hardware necessarily understood them. And so to sort of give some context to this, when I was about 14, 15, a good friend of mine and I were trying to take a game that was stored on cassette tape back in the day when that was a thing. You plug in a cassette tape into the port on the back of your computer, and the beeps and boops were like really low modem speed sounds. And then it would eventually load. It would take, 4 or 5 minutes and it would load. But we had disk drives, right? We were lucky that we had disk drives. We wanted to take the game that we had on tape and put it onto disk. But that meant hacking it.
Yeah.
Now, whether we actually legally owned the cassette tape that we were hacking it from is one for the pub. Although, in fairness, I have now met and spoken to the author, and I've kind of made my peace with him over this particular thing. But anyway, this was a particularly interesting hardware protection that was put on the cassette tape version. So effectively, the code was loading the beeps and boops from the cassette tape, and then it would jump to the beginning of the code. Now, I could write a piece of code that listens to the beeps and boops and gets this big block of code, And then I could probably just save it to the disk and then just run it. But it didn't work. And I forget for the reasons, and my friend Rich, who maybe listened to this, will perhaps remember why. But that wasn't possible. What you needed to be able to do is essentially decrypt and just pull out the bit of the code that you needed for the game. Now, the author didn't want you to copy it. The author didn't want you to put it on disk. The author didn't want you to look at his code, right? His admittedly compiled or assembled code. So he would write an encryption routine right at the beginning of where the program started executing. And that decryption routine would decrypt the game that was immediately after the decryption routine. So the code literally follows off of the last byte of the loop for all the bytes in the remainder, EOR with, FF, worst possible protection system, and then it would fall into the middle of the game. And there was no point in between those two where you could put a breakpoint or similar. And the reason for that was there were no hardware breakpoints. Yeah. And, the first thing you might want to do is you might want to modify the first byte after the end of the decryption routine to say, no, return here. But of course, you don't know what to write there because it's going to be decrypted. Right. So you have to write the encrypted return. Now, you could probably guess there's only 255 combinations. So you could try all of them. But then if you actually looked at the decrypt routine, you see that things that go into the key, I just said exclusive OR with FF, but the things that go into the key that decrypts the rest of the code are the bytes of the decrypted code, the bytes of the decryption routine itself. The decryption routine also modifies itself while it's running, so the key is mutating as it's going, and there's nowhere for you to poke in it. To stop you from doing like time-based attacks where you kind of stop it, jump out of there, and then patch up the routine, instrumented in some way, and then jump back to the beginning of that part of the routine that you patched out, it would use hardware timers. So there were timers that were changing variably as the thing was going on. It also would configure interrupts, and it wrote its own interrupt handler that deliberately did not leave the state of the machine alone. It came back from the interrupt routine having modified another part of the key. So where this interrupt was triggered and all that stuff all factored into it, which made it basically impossible.
So the guy built the Hellraiser cube into a cassette tape.
Effectively, that's exactly what he did. Yes, that's a perfect way of putting it. So, Richard and I, back in the mid-90s, we wrote an emulator for the very computer that we were writing an emulator on in the basic routine, basic sort of language of the computer that we had, in an attempt to emulate the protection system perfectly, or emulate the BBC perfectly, such that we could get to a point and then stop it and then save. Yeah. And we spent a couple of weeks on this and we gave up because it was just so complicated. All these things I just described to you were in this code. We'd have to be perfect, and they would have to be cycle perfect, like literally every tick of the clock. All these numbers are changing, hardware states changing, interrupts are being scheduled or descheduled or cancelled or not cancelled. And the whole thing was in there and it was brilliant. And we'd we can't crack it. So we gave up on it. But fast forward 30 years. Oh gosh. It really is. Fast forward several decades, and I'm writing an emulator for the same machine, but for recreational purposes, not for nefarious purposes. And I came across this game again, and I'm like, no, this time, game, I'm getting you, I'm having you. So one of the in addition to all the things we just talked about, one of the things that this particular protection system does is it used a rotate instruction. So rotate is like a shift where the top bit goes back into the bottom part. So bit 7 goes off and comes back into bit 0. And if you think and this particular rotate instruction was a rotate a memory address, which was unusual on the 6502. Normally you'd have to load something into a register, do something with it, and then store it back. But in this particular case, you could rotate directly a memory address. So if you think about what's happening inside that instruction, it's going to take several CPU cycles. It's going to have to read from that memory location. It's going to have to do something, and it's going to write it back out again. And this is all within a single instruction. Now, what Kevin's protection system did is it actually rotated the address of a hardware timer. So the hardware, this is a piece of hardware that pretended to be memory, but actually was not memory. It was a counting timer, and it was configured on the system such that reading would give you the current value of the timer, writing would reset the timer and start it again from that value, or something equivalent to that. So that's interesting. Now suddenly, in order to emulate this instruction perfectly, I have to emulate within the instruction, because as the instruction is executing, that timer is ticking down. So does it read from the timer on the 3rd cycle or the 4th cycle? Does it write to the timer on the 5th cycle or the 7th cycle, or what's going on? And so now you're assigned to answer. This was never put in any of the data sheets, to my knowledge, right? This is just like, no, a rotate takes 7 cycles. So how do you answer these questions, right? Unfortunately, I didn't have a 6502. Well, I did, but it wasn't in a BBC Micro. It was on a breadboard in front of me right here. But how do you answer these questions? And so this is when I went digging, and I discovered a whole world of folks who are taking chips, decapping them, that is, taking the protective plastic or ceramic layer off of the top of the chip, using extremely distressing chemicals to etch away at the plastic and the surface. Yeah. Really horrible stuff. I mean, there's terror stories out there for what happens if you don't look after yourself. So please, if anyone's listening to this, do not attempt any of these things.
Do not try this at home, kids.
Do not try. Exactly. But these people are doing this, and then they're using high-resolution metallurgical microscopes to take lots and lots and lots of extremely close-up photographs of the die. That is the actual integrated circuit that's underneath the plastic like chip that you would see if you saw a computer chip, right?
Right.
And then they're stitching those images together, and then using a combination of just brute force of human like line drawing, a bit of very primitive AI, and then a lot of head scratching. They are piecing together how these old chips worked. And what I'm talking about here is specifically enthusiasts that are doing this, as opposed to like the professional laboratories that will do this for like reverse engineering of competitors' project type things, which is definitely not in the scope of what I want to talk about. But these are like folks who are just more more relaxed around scary chemicals than most people, who are interested in this kind of stuff. And in particular, the 6502, because it was such an important processor, they targeted that first. So there's a website you can go to, visual6502.org, which shows you the high-resolution photographs and the polygonal data that they've extracted from those high-definition photographs, showing the different layers of the chip. And like these chips are old enough that the manufacturing process is visible under a high quality but affordable light microscope. Rather than anything kind of scanning, tunneling, electron nonsense, but also that there are few enough layers that it's practical for you to extract the layers one by one by like washing it in another and counting to 10, and then quickly washing off the solution and then looking at it again and like taking off these layers. There's a metal layer at the top, and then there's various layers of polysilicon, and there's various doped regions which sometimes you can see because they look a bit different. Other times you just have to infer that they're there. But the whole premise is that they have now a gate level, like I was going to say transistor level, really, it is what it is. It's a transistor level simulation of a 6502 that you can go and run in a web browser. And they've, moreover, as well as just emulating it and all the pads, that is the big connections that come off around the outside of the chip, there's been enough work that they can tag areas of the die and say, well, this is the A register. Right, wow. These flip-flops hold the A register. This is the X register. Here's all the other internal state. Here's how the PLL works. Here's how the instruction decode works. So with this information, they were able to explain comprehensively things like how the store AX instruction works. That SAX that we found?
Yeah.
They could trace the two low bits that I was talking about before, right. The 00, the 01, and say, well, what happens when the 1 and the 1's on? Well, this just activates the A register and the X register at the same time. Now, because of the way the physics works, and this is in the particular case of the 6502, it's an NMOS type of part, the sort of pulling low of a 0 wins out. So if there is a 1 being pushed onto like the output bus and a 0 being pushed onto the output bus because both the A register and the X register's kind of like enable has been turned on at the same time, then the 0 wins because it pulls the 1 down to 0. So that's the AND that you're getting. That's why it's store A and X if you put them both on at the same time.
Yeah.
Now, different fabrication would have come up with different other sort of side effects, but that's like one example of like that's what's happening in that particular instruction. So I was able to go to their site and do essentially a gate level or a transistor level simulation of the rotate instruction and see exactly what happens and what cycles the read happens and what cycle the write happens. And I was able to discover, and this was actually well known before this, I'm not discovering anything new here, but the in between the read and the write, there is a 1 cycle delay. While the chip is like thinking, it like reads a value into a temporary part of the chip, does the rotate the next clock tick, and then writes it out. But there aren't enough pins on the outside of the 6502 chip itself to sort of say, I don't need to read or write to memory this clock cycle. So it's always reading and writing from whatever the pins are.
Okay.
Right, so there are address pins and there are data pins, and there's 16 address pins, 8 data pins, and 1 read not write, which means that if it's high, I'm reading, and if it's low, I'm writing.
Okay.
So in this one in between step, the chip isn't doing anything, but these pins are still on the outside, and the RAM doesn't know that you're not talking to it or you don't care. And so normally it wouldn't matter, right? If it's no harm, no foul, it's like I'm reading or writing to a piece of memory that, okay, it doesn't matter. Or hopefully as long as you're not writing 0 to something. But it turns out that what's actually happening is it has already updated the address pins to, the address pins remain at the address of where it just read from.
Okay.
And the data bus still has the old unshifted value on it. But it's already toggled to write. So it's done a read the address, got a value 12 out, and then while it's doing its rotate, the microcode inside, it's not even microcode, but let's not get into that, but like the design of the chip inside, I said, well, we might as well toggle to a write ready to go, because in a minute we're about to write out whatever we're calculating. But of course what's really happening is a write of the old value has happened to the memory location it just read from. Okay, so far, no harm, no foul. Doesn't really matter, right? If you've just read from a memory location and you immediately wrote back to it, and then now you're going to update it with the shifted value, that's not a problem. Except, of course, if that hardware was hardware, it wasn't memory. Because writing to that address changes the state of the hardware you're writing to. And so this was a really significant find, because the timer that is actually on the end of this rotate gets 2 writes, and each time it resets itself. Now, you are about to write a new value over the top of it, but what happens if in that 1 clock cycle, the value you wrote to triggered the timer to go off? Now an interrupt's scheduled. And so this side-affecting write actually was important to model.
Interesting.
And so that was the first surprise. That was like, my gosh, okay, there's this redundant write that happens that's normally no problem, but now is important to model, and it was an important thing in getting this correct. Then there were some other things to do with the way the bus, specifically to the BBC Micro, worked in terms of slowing down. Did you ever go through the Apples? I know I'm frothing away here, but what did you have an Apple II or anything?
I had a Commodore 64.
Got it.
Yeah.
Do you remember if that had a 1 megahertz peripheral bus versus like a faster main CPU? I forget, and I know people will be shouting at their no, because I'm aware that the Apple had like a 1 megahertz 6502, and the 6502 can go faster than that. But the peripherals, which are all memory mapped, were all 1 megahertz. So they kind of just took the lowest common denominator and said, well, we'll run the CPU at the same speed as the peripherals, and then there's no problem. And later on, there were like aftermarket boards that you could plug into the Apple that sort of sped up the CPU. And then they detected when it was accessing peripheral memory, and they went, whoa, and they slowed the clock cycle down to match.
Yeah.
And that's what the BBC Micro did out of the gate. But that exact synchronization, when you imagine you've got like something running twice as fast, and it can be an even or odd cycle with respect to the 1 megahertz. And now also, this is happening every time it accesses these peripherals. So in that rotate instruction, not only is it having a side effect of writing to the 1 megahertz bus speed peripheral that's the timer, that slows the chip down as well, because it's like, well, I read once, that slowed me down. I wrote once, redundantly, that slowed me down again. And then finally I wrote the actual value that I wanted to write, and I got that through. And that was also slowed down. So like finding this out was amazing and a godsend, and piqued my interest entirely, because like staring at a bunch of seemingly hugely cryptic rectangular regions that don't appear to be connected in any way was somehow something the wizards could read and say, oh, that's an AND gate. And I'm like, what? No, it isn't. It's like, you highlighted that one green and that one red. Why did you do that?
Yeah.
Oh, well, this one's clearly doped this way because it's an even number of things from the outside. And I know and I'm like, what? How are you doing this? Well, this is witchcraft.
Yeah.
And as it happens, the 6502 is, and I'm probably definitely belittling the work that went into it, because it was a huge amount of work. But as I've learned a little bit more, the NMOS fabrication technology that was available to them in like the early 70s is easier to understand coming in from the outside. And you can sort of see, oh, that's a really big squiggly bit. That's probably a resistor. This bit over here is like a power transistor. This thing here with you can sort of see it if you squint. But again, it's one of those things where I don't know how often you have this experience when something you're being explained makes perfect sense while you're listening to the engaging presenter.
I mean, that's happening right now.
But then you're going to walk away afterwards and be like, that was really good, but I don't get it.
As long as there's not a quiz later, I'm completely fine.
Oh, right. No, that's it. No, it's I've had that experience with a whole bunch of folks. And so there's a number of people on YouTube that have like cataloged their reverse engineering of chips. There's Robert Baruch, if that's how you pronounce his name. There's a fantastic person, Ken Shirriff. Ken Shirriff has got a blog, and he does probably 1 or 2 a month where he tears down an IC or similar from like prehistory, usually, like something from the 70s or 80s. Like he's done 1-bit computers, he's done the 8088, 8086. And it's just super interesting and exciting, and it's written engagingly. And again, it's like a bit like you can let it flow over you, and you just appreciate somebody else understands this well enough to be able to do it and explain it well enough for you to at least understand how cool it is.
Yeah.
And so I've really loved that. It's been a really fun experience. And so, obviously it's touched me in terms of my emulation work. And then more recently, some friends of mine have started looking at a disk drive controller, which was something that came alongside the BBC Micro to control the disk drive. I mean, I know on the Commodore, for example, they actually just threw another 6502 inside the disk drive and said, well, that can just drive the disk and do all of the magic to understand how to shift the stepper motors in and out, and how to turn on the sense detection and all those kind of bits and pieces, and how to do the MFM and FM decoding. Which made it really an amazing target for like, well, here's a coprocessor. If it's not running the disk drive, surely we can do something else, which is exactly the kind of cool thing that, that was done back in the day. Because again, you could guarantee it on the end of a wire. I just loaded off disk. I got a spare 6502. Brilliant. Now, the disk controller that my friend took apart is an Intel disk controller. And it's long had this, again, a big list of here's the commands you can run. You're like, well, there's a gap. Somewhere in this list of I wonder what it does.
Right.
But yeah, through decapping it and getting a friend to photograph it and then go over it, they were able to isolate an area which looked like ROM. And so it became clear that it was basically a CPU, an embedded CPU, probably with a very strange opcode list, but they were able to isolate where the ROM was. And then using some real tricks of like known bytes that were written to the disk drive when you like format it, for example, they were able to like find regions of the ROM that corresponded to that, and then theorize and later on essentially reverse engineer the opcodes for this CPU that was the drive controller that lived inside the BBC Micro's disk drive system.
Wow.
And I mean, that's just amazing. And I love that kind of stuff. It's just so interesting that there's always a layer lower than where you are, right? You can be, you can be writing in high level language and be vaguely aware you're interacting with an operating system. You could be writing an operating system and you could be using C++, or you could be using C, and you'd be thinking like, yeah, I'm laying memory out. I know exactly what I'm doing. And then you're like, well, there's a DMA controller that can also read and write to memory, or the network card can also read and write to memory. And there are interrupts. And, you kind of think, well, okay, I know where I am with interrupts. Okay, I've written an interrupt handler. I've written games before, and I've kind of had to feed the graphics unit by every time it ran out of work. I would, all these cool things. And you think, I'm talking about myself here. Like, I think I've reached the bottom of the stack now.
Yeah.
I've written an interrupt handler. That's it. We're done now. It's like, when Lord Kelvin said, "There's no more physics. We're done here." But then you go, no. There's more. You can dig down, and on Intel processors, you can go, well, there's microcode. What you put into the processor is not even remotely what it actually executes. You're like, oh, really?
Mm-hmm.
Well, that's fascinating to me. How do we know? How can we observe it? And, there are all these clever tricks. And you kind of start learning down further and further in optimization. And you're like, wow, that's amazing. And then somebody else comes along and blows your mind by saying, you can take the lid off that chip.
Yeah, right.
See how it works inside. And like, oh my gosh.
Yes.
It's so cool. It's so cool. And I've really enjoyed the journey, and I'm still learning an awful lot about this, but it's just a lot of fun.
So how do you think that going back to the game that you were trying to crack, how do you think Kevin was his name? You said you talked to him, right?
Kevin Evans, yes.
Yeah.
Yes. Oh,
how did he figure out all these things? Because if you didn't figure it out for 30 years later by stripping the top off the chips, how in the heck did he do it?
That is a splendid question, and one that we thought for a long, long time about. But my friend Rich was able to theorize how he did it and got him to reply on a forum post that indeed that was the case. And through that, we've become, I wouldn't say buddies, but we were acquainted now, which is great, right? They say don't meet your heroes, but I've had some great experiences with the people who are writing video games in the late 80s, early 90s. Probably because they're only a couple of years older than me, even, right? It's not like they're that far ahead of me, in age terms at least. But yeah, so the way that he did it, so the way that it actually went, I simplified it a little bit earlier, obviously for the purposes of explanation. But what really happened is that the decrypt code ran, and it landed not in the game, but in a CRC check. And that CRC checked the CRC of the decoded game. And if it didn't match the expected known plaintext CRC, it jumped to the ROM routine that wiped all memory and reset the computer.
Mm-hmm.
Okay, so there was still no way. You couldn't go in and say, let's take out the jump to the reset and kind of get in there. Because, again, the CRC code itself, that is the bytes that implemented the CRC, were part of the key. So by modifying it to say, hey, don't do that, you would destroy the key and it wouldn't decrypt correctly and all that stuff, right? So essentially any minor perturbation to the code anywhere would either crash it, or it would get to the end of the decode routine, the CRC check would fail, and it would wipe the memory of the computer, and it would have to start again loading it off tape for another 4 or 5 minutes of your life, right?
Mm-hmm.
And so Richard theorized that Kevin had desoldered the ROM on his motherboard and replaced it with a ROM that did not wipe memory when you jump to it failed the CRC routine.
Oh.
So far, so okay. How do you use that to help, right? Because you run it, and if the CRC was wrong, well, it would just reset the computer, but the memory would be okay still.
Yeah.
The second thing that Richard realized is that the way that the cipher worked, essentially, is cyclical. It's like a random number generator style, like encryption key generator, right? Dynamic, but cyclical.
Mm-hmm.
And so it would repeat after a certain amount of time, certain number of iterations. So what the process is Kevin loaded up this decrypt and CRC, put the known CRC of the unencrypted game into the CRC code, because that's how that's how it should. That's how it knew it got the decode right.
Yeah.
And then he put the unencrypted game after it, and then he put in his desoldered ROM with the don't wipe memory, and he executed it once. So what of course happened is that the decrypt code ran on the unencrypted game and caused it to change in some totally unpredictable way. But critically, the same way every time, and in a way that if you were to continue doing it, it would eventually cycle back to where it started.
Oh, okay.
So then it would get to the CRC code. The CRC code would fail, and it would reset the machine but keep everything intact. Kevin would save that image to disk, and then he would run it again. And then he would run it again and keep running and saving and running and saving. And every time it reset, he knew that he was another iteration along.
Is it the idea here that eventually it cycles back around and then you get something? Yeah, okay.
And then, on the last iteration, it would cycle back to the beginning. The CRC check would complete, and it would jump into the game. And of course, at that point, he was locked out. You couldn't do anything, but that's fine because he kept the previous iteration's disk image, and that was the one that was sent off to be fabricated.
Right.
So he himself doesn't understand how his own code works, right? He still doesn't understand. I mean, he does because we've talked about it, but at the time that he made the code, all he knew was that it was deterministic, and that it would be enough repetitions of that decrypt code would eventually cause it to repeat back to where it started from. And I think that's just genius. So it was both, an incredible piece of engineering in the first point to think of all the things that a hacker would use, timers and counters and, self-modifying code and, all this kind of nonsense to stop them from hacking it. It was understanding enough about the way that this particular type of encryption works that it would cycle. And it was, at the end of the day, desoldering something off the motherboard of your machine and replacing it, which nobody thought of.
Wow.
It's so cool. It's so cool and so interesting. And yeah, I'm glad to say that JSB will run the Alien 8 protection system. And in fact, Kevin gave me permission to make it a test. So we can get back to testing. One of the tests is to actually run all of that I just described and make sure that it gets to the end and executes the first byte after the CRC code, which incidentally, I don't even have, right? The rest of that code is it stops here. There's not enough for it to be the game. So it's just the code, but it's so fun. It's so cool. And there's so much to learn from it. And this is, again, 45-year-old computer now.
Yeah.
Quite amazing. Not 45. Gosh, no, I'm 45. 35-year-old computer. That's slightly better.
Yeah. Wow.
So do you have any experiences like that? I mean, we've talked that at, late teens, early 20s, our paths diverged.
Yeah. No, I was not into hardware at all as a kid. I mean, I was very much into, I learned how computers work mostly to play games because it was not exactly a straightforward thing back then to,
You mean Hymen.sys?
Yeah,
programming.
Figuring out what the heck was wrong with my sound card and all of that sort of stuff. That was my first
moving
real...
jumpers.
Yeah, exactly. That was my first real attraction into it. And so, for me, it was about, when I was a kid, my dad owned this software company. It's kind of how I got into it, that did audio video processing. And so
I can't believe I never knew that.
Yeah.
That's so cool. We're going to have to talk about that sometime.
Well, yeah. It was amazing for me as a kid because I got access to, computers and I had high-end video cards to do video capture. He'd built a system for digital editing. I mean, now you can do it on your phone, but back in the early 90s, late 80s, it was something unique.
Gen lock boards and things that were that kind of nonsense. I remember at the time TV shows that we will watch, the music TV shows would be using the same kind of technology that you're talking about to do their on-screen graphics and silly you had that in the basement or wherever.
Yeah, let me tell you, I had some really amazing video presentations as a grade schooler when I was a kid. I was just blowing the other kids away. It was kind of unfair, actually. But yeah, so I never really got too much into hardware until very much later in life. I mean, it was really 10 years ago, and it was Arduinos, and I built this little house temperature environment monitoring system with Zigbee radios. And,
nice.
Stuff like that. But it was always just a hobby thing for me as an adult. It's never something that I really did as a kid. I mean, I had little electronics kits and stuff like that. Make the buzzer go off, make the light go off, but nothing really serious. So this has been sort of more of a for something to me later in life. Early was all about software and to, I guess, to some extent, some of this video hardware, but it was all super specialized. I never really got down into the bits and bytes. It was all about, if I take this video stream and I blit myself on top of it, that sort of stuff.
Right. But I mean, it's just so much interesting stuff going on with hardware. And thinking, I mean, outside of the box, and that's what I love the most about the both the emulation and the sort of hacking side of the of that, was like, you really have to think, how could I achieve what I need? Maybe not by not using the manuals, maybe by using some other observable thing. It forced a lot of problem solving, which I think ultimately, if you strip away everything about what I love about our job and what I do as a hobby and what I do in my evenings when I'm not doing my hobby, it's problem solving.
Yeah.
In a sort of constrained environment as well. I think that's what makes it more interesting. Like if you've got like no real constraint, then you just kind of do the next obvious thing. But if you're like, no, I have a 2 megahertz 8-bit computer and I want to do ray tracing, you kind of have to pull something magical out to make it work, and that's kind of it. And
I was gonna say, it's sort of like there's two kinds of people in the world: people who watch Apollo 13 and are compelled by the story, and people who watch Apollo 13 and are like, man, I really want to figure out how to get that air filter into that square hole, right? Like, you're like, really, like, I want to know
exactly
how did you figure it out? You had the things of the thing. And yeah, that sort of mentality is kind of unique, and it's super fun when you have those sorts of problems that are like, all right, guys, we have 90 minutes to figure this out. These are the materials you have. It has to fit into this box. Go, right? Yeah.
And I mean, sort of just to try and sort of give something out that our listeners can play along with, rather than just listening to me babble on at this kind of nonsense. There's things that you mentioned, actually. Like if any of this is interesting to people, I'm sure you can Google and find a lot of this stuff. Reverse engineering chips. Ken Shirriff's blog is great as well, I think, which is rito.com. But you mentioned Arduinos. There's Raspberry Pis, there's Arduinos. And in fact, like the Raspberry Pi very specifically is modeled on the BBCB, because the founder of the company was like, I don't have a way to hand to my children the same experience that I had when I was hacking around on my BBC Micro. It was at school, I had one at home. It has all these vague, weird ports hanging out the back, which was another sort of like relatively unusual thing about the Beeb. You could put a ribbon cable on the back of it, and then you could like plug it into turtles that draw lines on the ground, or hardware things. And magazines would even have like printable stuff. I remember having like an 8 element LED wand that you could build, and there was inside of it was a like a motion detector, or actually it was a mercury switch, and so it could tell how quickly you were waving it backwards and forwards. And for those listening on the podcast and not looking at me in the video, which is only Ben, I'm wiggling my hand backwards and forwards like I'm batting a bat. And so and then it allowed you to like write a message in the air by serializing out and turning on the LEDs, and that was so cool because I was building with a regular computer. So anyway, that exposure to hardware and the low level and and just hackability was what inspired the Raspberry Pi. And so I feel like there's a nice warm glow I get from like realizing that now on my desk here, as you can vaguely see just at a shot, I have a whole bunch of Raspberry Pi related gear because I'm hacking on this kind of stuff again, and it's brilliant. And so people can get Raspberry Pis, they can get Arduinos. The Arduino IDE in particular is just really, really user friendly.
Yeah, it's
you can
great.
Go write an emulator, you can hack around with this hardware, and there's just a lot of cool things that people can still do this nowadays, even though it feels, as we're staring at these huge supercomputers in front of us, well, even the ones that we have in our pockets are supercomputers by anyone's yardstick. These are all, there's still an accessible route to playing around with interrupt handlers and assembly and just understanding at a deeper level how computers actually really work.
Yep. Yeah, it's super fun. And I love it when you can kind of solve a problem that you have with some of these devices. It's really amazing. And if you can get your kids interested too, that's a huge bonus. But.
Well, for us, that's a big deal, right? If you can get them to see that life isn't all Minecraft and it isn't all Roblox. You can do a real thing with a relatively small amount of code and get something interesting happen. And as I'm saying this, my son has just popped his head around the corner and is looking at me quizzically like, no, I won't. It's like,
yeah, right.
I missed that boat.
Well, redstone is the gateway drug. So if your kids are into Minecraft and they're playing around with redstone, you'd be like, how would you like some real life redstone?
Well, that's the funny thing.
Yeah.
I did a sort of passive aggressive parenting technique of buying some sort of textbooks on CPU design and on physics and on I can't remember the other, but they were like manga style ones, and I left them around the house.
Nice.
And then my eldest did pick it up and kind of read enough of the CPU stuff for two things. One thing was for him to go, hey, this is just like redstone, which is like the biggest compliment we could get. Is like, well, you understand enough about how redstone works, and you were able to see it out of context in like a truth table, in admittedly in a manga style, but a relatively dry text. And then the other thing is he found how numbering systems work in binary, and he said, pointing at the thing, he goes, for signed numbers, going like, oh, I see where you got the name of your podcast now.
Yeah.
So like the circle is now complete.
The circle is complete.
All right, my friend. Well, it's been so much fun. Thank you for letting me froth and talk excitedly at you. And I mean, it would be
this is great.
fascinating if our listeners or listener, however many we've got, found this interesting too. If we haven't just alienated everyone, then I'd be surprised. But I mean, I'm just hoping that the enthusiasm which I feel for this subject comes across, and some, at least one person is inspired to go and have a look or hack on some hardware or dig down through the chip layers or read up how their CPU isn't really doing what they're telling it to do. It's a deep, deep subject, but I guess we can talk about other things another time, right? I mean,
different topics every week. That's what we should do. I dig it.
You reckon? Okay.
Yes.
It's a deal, my friend.
All right.
Talk to you next time.
Cool. Yep.
You've been listening to Two's Complement, a programming podcast by Ben Rady and Matt Godbolt. Find the show transcript and notes at twoscomplement.org. Contact us on Twitter at 2CP, that's at TWOSCP. Theme music by Inverse Phase, inversephase.com.